For several years, Skoda has been fitting efficient and powerful diesel engines to their vehicles. However, the demands to reduce emissions further whilst improving performance, fuel economy and noise levels are constantly growing. The key factors in meeting these requirements are better mixture control and improved fuel atomization. Both requirements call for an efficient injection system capable of producing extremely high pressures whilst at the same time precisely controlling the timing and the volume of fuel delivered into the cylinders. Back in 1905, Rudolf Diesel had the idea of combining the fuel pump and the injector into one unit. This removes the necessity for high-pressure connecting pipes between the injection pump and the injectors, thereby allowing the injection pressure to be increased. However, it wasn't until the 1950s that the idea of pump injection came to fruition when it was introduced into the shipping and haulage industries. It became known as mechanical pump injection, or the pressure time system. Mechanical pump injection alone is capable of producing higher fuel pressures which lead to finer atomization. But by adding a computer-controlled solenoid valve to each injector to regulate the fuel quantity and injection timing, the ideal system is born. For the first time, the Volkswagen Group with Skoda and in association with Robert Bosch AG have developed passenger car diesel engines that incorporate a solenoid-controlled pump injection system. The system, known as pump-nozzle, that's pump injection in English, is fitted initially to the 1.9-litre four-cylinder diesel engine. Perhaps not surprisingly, with a diesel injection system that's technically so advanced, it's essential that technicians are aware of its main features. So we hope that you'll find this program to be both interesting and helpful. Section 1 looks at the fuel delivery system. Section 2 covers the fundamentals of the pump injection system. Section 3 describes the engine management system. And Section 4 highlights the engine's main mechanical and self-diagnosis features. You'll also find additional detailed information in Self-Study Program 36. Section 1. Fuel Delivery. The fuel delivery system, which is completely different to previous systems, comprises submerged electric lift pump in the fuel tank, fuel filter, non-return valve, mechanical fuel pump with limiting valve, supply line, return line, pressure regulating valve with bypass, temperature sensor, and a fuel cooler. The function of the submerged electric pump is to lift fuel from the tank and deliver it via the fuel filter and non-return valve to the main mechanical fuel pump. The non-return valve prevents fuel from returning to the tank whilst the engine is stationary. The mechanical fuel pump is of the blocking vane cell type. It's located at the end of the cylinder head directly behind the vacuum pump, and the camshaft drives both pumps simultaneously. From the pump, the fuel is directed via the supply line to the injectors. The pump also includes a pressure limiting valve that opens should the supply line pressure exceed 7.5 bar. Excess fuel from the injectors returns to the tank via a pressure regulating valve within the pump. The valve maintains a constant return line pressure of 1 bar. Note also the bypass channel, which acts to bleed air from the system should the vehicle run out of fuel. From the regulating valve, returning fuel then flows to the temperature sensor and then on to the cooler before eventually arriving back at the tank. The fuel cooler plays an important role in the system, as without it, the high fuel temperatures created by the sudden pressurization within the pump injectors could damage certain components and may affect the volumetric efficiency of the engine. The cooler is located in the fuel return line under the car and uses the ambient air to absorb the heat. Section 2. The System Fundamentals. Pump injection, as its name implies, is simply an injector and pump combined in one unit. With this system, each cylinder has its own dedicated pump injector unit. The engine's camshaft operates the plunger-type pump injectors via additional camshaft lobes and roller rocker arms. The pump operation is simple. As the camshaft rotates, the rocker arm forces the plunger downwards, compressing the fuel. The extremely fine atomized fuel is then delivered directly into the cylinder. Good mixture formation is a prerequisite for efficient combustion. Therefore, the precise quantity of fuel must be injected at a high pressure and at the correct time. Furthermore, to help reduce noise or diesel knock, which is caused by the sudden increase in combustion pressure, it's best for the fuel to be injected in stages. The first stage injects only a small quantity of fuel and is known as the pre-injection cycle. This pre-injection reduces the sudden rise in combustion pressure, thus helping to reduce knock. The second injection stage is called the main injection cycle and delivers the principal charge. A solenoid valve controlled by the engine control unit determines both the timing and the duration of the injected fuel. The injection cycle starts with the filling of the high-pressure chamber. As the camshaft lobe rotates, the pump piston is pushed upwards by the injector spring. Because the solenoid valve is open, fuel under supply line pressure flows into the chamber. As the cam rotates further, the pump piston is forced downwards, displacing the fuel from the high-pressure chamber back into the supply line. At the correct moment, the engine control unit activates the solenoid, closing off the fuel's exit to the supply line. Thus, fuel remaining in the chamber becomes pressurized. When it reaches 180 bar, the injector needle lifts and the first stage of fuel injection commences. This pre-injection cycle soon ends. This is because the increasing chamber pressure forces a small reaction piston downwards, thereby increasing the tension in the injector spring, and as a result, the injector needle momentarily closes. Meanwhile, because the piston is still moving downwards, the chamber pressure continues to rise. When it reaches 300 bar, it overcomes the increased tension of the injector spring, causing the needle to lift for a second time, and the main injection cycle commences. Because fuel is pumped into the chamber at a far greater rate than it can escape through the nozzle, the chamber pressure can reach 2050 bar. This high pressure provides excellent atomization. The main injection cycle ends when the control unit opens the solenoid valve, allowing the highly pressurized fuel to escape back into the supply line. By the way, the high-pressure chamber always receives more fuel than required, and this excess fuel is directed back to the tank via the return line. The returning fuel cools the pump injector units and removes any trapped vapor bubbles. Hopefully, you now appreciate that the operating principles of the system are both ingenious and yet fairly straightforward. Section 3. The Engine Management System. Like many of today's fuel systems, the pump injection system relies on an advanced processor-controlled engine control unit. The control unit receives input data from numerous sensors and several auxiliary signals. It also constantly exchanges information via the high-speed drive CAN network with other control units, such as those of the ABS, automatic gearbox, and instrument panel. In addition, the engine control unit, via the gateway, can communicate with control units connected to the lower speed comfort CAN, including that of the air conditioning system. You'll find more information about the two CAN networks and gateway in SSP 33. The engine control unit is also responsible for controlling various actuators, including the electric fuel pump and the PTC element for interior heating. And for diagnostic purposes, it can communicate directly with the VAS 5051 or VAG 1552. Many of the system's input sensors, such as the air mass meter, may be familiar. However, the way in which some of their signals are utilized is a little different to previous applications. So let's take a look first at those which monitor the movement of the crankshaft and camshaft. To activate the appropriate pump injector solenoid valve on starting the engine, the system must be able to determine which cylinder is on the compression stroke. The information is provided by the hall sensor, G40, positioned just below the camshaft sprocket. It scans the sensor wheel teeth as they rotate with the camshaft. Each cylinder is identified by a unique tooth arrangement, ranging from a single tooth for cylinder 4 to two teeth separated by a 30-degree gap for cylinder number 1. By comparing the hall signal against the signal received from the crankshaft position sensor, the system can calculate which injector solenoid to activate first. If the hall sensor signal fails, then the control unit utilizes the engine speed sensor signal instead, allowing the engine to continue to run. The engine speed sensor, G28, is a permanent magnetic inductive device. It monitors a sensor wheel that's attached to the crankshaft. Around the sensor wheel's circumference are 59 teeth and 2 gaps. The gaps are offset by 180 degrees, and these provide the crankshaft position signal. The 59 teeth supply the control unit with engine speed information. Should the engine speed sensor fail, no substitute value is available, and therefore the engine will stop. Now let's consider the temperature sensors. The system incorporates 3, one of which is used by the control unit to calculate fuel density. The density, which varies according to temperature, needs to be taken into consideration when determining the injection timing and the quantity of fuel injected. The fuel temperature sensor is located in the fuel return line. If the sensor signal fails, the control unit calculates a substitute value by using the signal from the engine coolant temperature sensor. The signal from the engine coolant temperature sensor, G62, is used in controlling the glow plug circuit and to calculate the fuel injection quantity during the warm-up period. Should it fail, then a substitute signal from the fuel temperature sensor is used instead. For the control unit to regulate the turbocharger's boost pressure, it utilizes two sensors. They measure the temperature and the pressure in the intake manifold. Both sensors are integrated into one component, and a loss of performance will result should either sensor fail. A familiar yet extremely important sensor is the air mass meter, G70. As with most engine management systems, values from the sensor are used in determining the fuel injection volume and the exhaust gas recirculation rate. To cope with altitude changes, the pump injection system incorporates an altitude sensor within the electronic control unit. Its signal is used to control precisely the boost pressure and exhaust gas recirculation systems, etc., according to altitude. One of the most important input signals comes from the accelerator position sensor. It informs the control unit on how much power the driver is requesting. Note that the idle switch and on automatic vehicles the kickdown switch are incorporated within the same component. Failure of the accelerator position sensor will cause the driver to lose all accelerator response. However, the idle speed will be automatically increased, allowing the car to be driven slowly to the nearest dealer. For safety reasons, if the accelerator position sensor fails, the engine's power is restricted during braking. The brake light switch and a brake pedal switch combined in one unit provide the brake-activated signal. Note that if either switch fails, the control unit will automatically reduce engine power. The system also incorporates a clutch pedal switch, the signal from which is used to prevent engine shudder when shifting gear. Again, if the switch fails, the engine power will be reduced. The control unit also receives additional signals from other areas of the vehicle, such as the air conditioning system and from the alternator, to inform on its output. Other auxiliary input signals come from the cruise control system and the road speed sensor. Probably the most important components of the pump injection system are the injector solenoid valves. They are used by the control unit to determine fuel volume and injection timing. For example, by extending the duration for which the valve is energized, more fuel will be injected. Reducing the energization time results in less fuel being injected. Similarly, by energizing the solenoid either earlier or later, the point at which the fuel is injected can be altered. Closing the solenoid valve earlier will advance the injection timing and vice versa. A common characteristic of diesel engines is the shudder that occurs when the engine is turned off. It's caused by the high compression pressures in the cylinders. To help overcome this, the engine incorporates an intake manifold flap which interrupts the air supply as the engine is switched off, so helping to eliminate the shudder. The vacuum-activated intake flap is controlled by a changeover valve, N239. Intake manifold boost pressure is provided by a turbocharger with variable turbine geometry. Its output is regulated by the engine control unit via the charge pressure control valve. The valve receives from the control unit a variable duty cycle pulse, the width of which determines the quantity of vacuum reaching the diaphragm of the turbine vane actuator. For more detailed information regarding variable turbine geometry, please refer to Self-Study Program 22. As you might expect, to help reduce oxides of nitrogen emissions, the engine also includes an exhaust gas recirculation system. It's regulated by the engine control unit via an exhaust gas recirculation valve. The engine's glow plugs are also controlled by the ECU, and their operation depends on input signals from the engine speed and coolant temperature sensors. The ECU controls the glow plugs via the glow plug relay located in the relay carrier. The system operates as follows. When the ignition is turned on, the engine control unit checks the coolant temperature. If it's below 9 degrees C, then the glow plugs and the warning lamp are switched on. When the light goes out, the engine can be started. To help reduce noise, exhaust emissions, and to improve idling immediately after starting, an afterglow phase always takes place. Afterglow lasts for no more than 4 minutes and is interrupted once the engine reaches 2,500 RPM. To improve driver and passenger comfort shortly after starting the engine in cold weather, the heating and ventilation unit includes an electric heating element. The PTC-type element is located next to the normal heat exchanger and directly warms the air entering the car's interior. Depending on the available spare capacity of the alternator, the engine control unit can switch on, via 2 relays, 1, 2, or all 3 of the heater's elements as required. Most modern engine management systems pass on signals to other areas of the car, and the pump injection system is no exception. For example, it supplies engine speed signals to the rev counter and fuel consumption data to the multifunction indicator. It's also responsible for controlling the cooling fan run-on period. So that completes our look at the pump injection management system. In the next and final section of the video, we'll look at the engine's mechanical features and fault diagnosis. Section 4. Engine mechanical features and fault diagnosis. Mechanically, the new 1.9-litre pump injection engine is based on the 4-cylinder TDI engine used in the Octavia. The new engine produces 74 kilowatts of power and a staggering 240 Newton-meters of torque. It's equipped with a turbocharger and intercooler, exhaust gas recirculation, and an oxidization catalyst. Because of the high combustion pressures, these engines use trapezoidal pistons and conrods. The trapezoidal design allows the high downforce acting on the piston crown to be distributed across a wider bearing contact surface. The pump injectors are capable of generating an injection pressure of about 2,000 bar. To rotate the camshaft against such pressures requires a large force. And because of this, the toothed belt and its drive mechanism have received some design changes. For instance, the belt is 5 millimeters wider than in previous models. The camshaft sprocket incorporates a vibration damper. And to prevent rapid belt wear, some of the teeth on the crankshaft's sprocket have slightly wider spacing. This is why. During the injection cycle, the high pumping forces stretch the toothed belt and temporarily increase the pitch of its teeth. This could cause the belt to be pinched. By increasing the space between these particular teeth, the momentary change in pitch is compensated for and the belt is no longer pinched. Incidentally, by using a hydraulic tensioner, the constantly changing loads within the belt are also automatically compensated for. If replacing the belt, then always refer to the workshop manual, but this is basically how it's done. Firstly, remove the crankshaft pulley and toothed belt covers. Next, turn the crankshaft until the mark on its sprocket is at the top. And the 4-cylinder arrow on the belt guard aligns between the two lugs on the camshaft's sensor wheel. To prevent any movement, the camshaft and crankshaft should be locked using the special tools. When fitting the crankshaft tool, it's important that the reference mark on the sprocket aligns with that on the tool. Next, using the pin wrench, hold the tensioning roller whilst releasing its securing nut. Then turn the roller anti-clockwise until it reaches the stop. At this point, insert the special tool to lock the hydraulic tensioner's push rod. Now turn the roller clockwise to the opposite stop. The idler roller and the toothed belt can then be removed. Note that if reusing the belt, mark its direction of rotation before removal. To refit the belt, start by loosening the camshaft sprocket's securing bolts and align it so the bolts are in the center of the elongated slots. Hand tighten the bolts to remove any free play. Install the toothed belt by placing it in sequence around the camshaft sprocket, tensioner roller, crankshaft sprocket and water pump. The idler roller can then be refitted. Now turn the tensioning roller anti-clockwise until the locking plate can be removed from the tensioner's push rod. Next, retension the belt by turning the roller clockwise until there's a 4 millimeter gap between these two components. At this point, retighten the securing nut to the correct torque. The camshaft sprocket bolts are then tightened and the mandrel and crankshaft stop can be removed. Turn the crankshaft twice in the direction of normal rotation and back to the TDC position on cylinder number 1. Now verify the setting by inserting the crankshaft locking tool and the camshaft mandrel. Finally, check the gap at the hydraulic tensioner and if incorrect, readjust the tensioning roller. After making any corrections, always rotate the crankshaft twice and recheck the settings again. Now let's look at the onboard diagnosis features. For demonstration purposes, we'll use the VAS 5051. The diagnostic capabilities are advanced, to say the least, and incorporate a unique method of testing for faulty injectors. It's carried out by measuring the current draw of the injector solenoid valves. At the point where the valve closes, a distinct knee appears in the current draw curve. The knee is used by the ECU as an indication of the beginning of the injection period, referred to as BIP. If the self-diagnosis system detects that the BIP is out of tolerance, the ECU will record a fault code in its memory. On this vehicle, a fault has been detected with the solenoid or circuit of number 3 injector unit. The next step is to confirm the fault by using the function 08, read data block. Entering the display group 018 allows fast verification of injector solenoid faults and should always be referred to when an injector solenoid fault code is recorded. It displays a status value for each cylinder, the specification of which should read 0. If anything other than a 0 is displayed, it's an indication of air in the fuel delivery system, or that there's a problem with the applicable injector solenoid and/or its associated wiring. A full explanation of the correct diagnostic procedure can be found in the workshop manual. However, it's always a good idea to start by eliminating the possibility of faults within the fuel system. During the process, you will need to test the supply line pressure. It's done by connecting the appropriate pressure gauge to the service connection point on the pump and then starting the engine. Compare the pressure with the specification in the manual. Contaminated or poor quality fuels can cause erratic running, idling and stalling problems, particularly when hot. So if in doubt, running the engine from a temporary alternative fuel supply will quickly verify if poor fuel quality really is the actual source of the problem. Initial testing of the injector solenoid and its wiring can be done by checking the injector's resistance value and its wiring for continuity. Alternatively, you can compare the injector solenoid's oscilloscope waveform with that of one from a known good cylinder. If you do suspect that the system has a faulty injector solenoid, then always confirm the diagnosis by exchanging the suspect injector unit with one from an adjacent cylinder. If the fault moves to that cylinder, it will confirm your diagnosis. Providing you follow the procedure in the workshop manual, replacing an injector unit is straightforward. Start by removing the belt guard and cam cover. Turn the engine until the camshaft lobes on the cylinder of the defective injector are pointing upwards. Then slacken the locking nut and unscrew the adjusting screw until the bottom edge of the rocker arm contacts the injector unit spring. Next, remove the rocker shaft securing bolts, starting from the outside and working inwards. And then lift off the shaft. The injector unit's tensioning block can be removed next. After removing the wiring plug, carefully position the special slide hammer and then withdraw the injector unit from the cylinder head. Note that replacement injector units are supplied complete with new oil and heat shield seals. If for any reason the old unit is being refitted, always follow the instructions in the workshop manual and replace all seals. Check that the seals are not twisted and then carefully push the injector unit fully into the cylinder head. Next, fit the tensioning block into the slot on the side of the injector unit. Note that if the injector unit is not fitted at 90 degrees to the tensioning block, then serious damage to the cylinder head will occur. Therefore, using a vernier gauge, check the distance between the injector and the outer edge of the cylinder head. The correct dimensions for each cylinder are specified in the workshop manual. Once aligned, follow the instructions in the manual and tighten the securing bolt and refit the rocker shaft. Now the injector unit must be correctly adjusted to prevent the pump piston from contacting the bottom of the high-pressure chamber. Align a dial gauge on top of the injector's adjusting screw and then rotate the engine until the rocker arm is fully down and then remove the gauge. Now turn the adjustment screw clockwise, thereby depressing the spring until a firm resistance is felt. At this point, unscrew the screw 225 degrees and then tighten the lock nut. In addition to reading, confirming and erasing BIP fault codes, the self-diagnosis system incorporates all the familiar diagnostic functions, including final control diagnosis, which on this engine must be initiated with the engine running. It activates various actuators and is particularly useful for testing, for example, the operation of the EGR valve, charge pressure control valve, intake manifold flap changeover valve, glow plugs relay, and so on. As we demonstrated earlier, a particularly useful feature for fault diagnosis is function 08, known as Read Data Block. In this function, around 18 display groups can be entered. In addition to display group 018, already mentioned, display group 000 contains data unique to the pump injection system, and therefore it may be new to you. Display group 000 is especially useful when conducting a quick system health check. It calls up 10 values indicating engine speed, commencement of injection, accelerator position, quantity of fuel injected, intake manifold pressure, atmospheric pressure, coolant temperature, intake manifold temperature, fuel temperature, and air mass value. The test conditions and the specifications for the values can be found in the workshop manual. Instructions on what to do if any of the values are incorrect is also supplied. If the need ever arises to replace the engine control unit, then remember these important points. Firstly, using function 07, code the replacement to match the engine and country. Then use the adaptation function to match the control unit to the vehicle's immobilizer system. In this final section of the video, we've highlighted only the most significant and new features of the self-diagnosis system. Remember that further in-depth information on all diagnostic functions, together with their test procedures and specifications, can be found in the applicable workshop manual. By using the latest in mechanical design and microprocessor technology, the electronically controlled diesel pump injection system is capable of meeting not only the current demands, but also those of the foreseeable future, and heralds a breakthrough in passenger car fuel system design.